So tonight we're going to look at the inverse of a function. We looked at lots of characteristics of a function, but every function has an inverse. I love how the regents of New York describe what a function and an inverse are. A function and its inverse can be described as the do and the undo functions. A function takes a starting value, performs some operation on the value, and creates an output. The inverse takes that output, performs some operation on it, and arrives back at the original function's starting point. There are three ways that we're going to look at finding an inverse. The first one is algebraically. The second one is tabular. The third one is graphically. The one thing I want to make sure that you do understand is that not all inverses are functions. So pause the video and copy currently what's on the graph. Typically, the rule is if it's a graph, it must be on graph paper, but you can freehand draw these graphs. The first thing we want to learn is how to test whether a graph is a function, which we did last night, but also whether the inverse of that graph is a function. And I can tell that from right where we are here. So we learned yesterday that the vertical line test tells me whether a graph is a function. This graph is a function. I only hit one time. This graph is a function. This graph is a function. So the vertical line test will tell me whether or not my graph is a function. Right from this diagram, I can know whether or not this particular graph, whether the inverse is a function, whether the inverse of this graph is a function. And I do that by doing the horizontal line test. Doesn't hit twice, so that graph, the inverse of this graph, is a function. I hit 2 times, so the inverse of this graph is not a function. I only hit once, so the inverse of that graph will be a function. So the horizontal line test will test whether the inverse of the graph is a function. So one more time. I can test whether or not a graph, so the green graphs here, are functions by doing the vertical line test. If it hits more than once, then it is not a function. If it doesn't hit more than once, then it is a function. I can also tell whether the inverse of this green graph is a function by doing the horizontal line test. If it doesn't hit more than once, then it is a function. This hits twice, so the inverse of this green graph will not be a function. So in order to find the inverse algebraically, all I do is switch the x and the y. Nothing else, just the variables. So I would rewrite this as x equals 2y plus 7. And now I solve for y. So I'm going to subtract 7, multiply by the inverse, distribute, and make sure that this is the inverse of y. We denote inverse by that right there, to the -1. Let's try this one over to the right. So again, the first thing I'm going to do is just physically switch the x and the y. And now solve for y. Well, what's the first thing I need to do here is I need to get the y out from under that long square root, so I'm going to square both sides. and I get x squared equals 3y plus 1. I'm going to subtract 1. I'm going to multiply by the inverse. And make sure that it's the inverse. Pause the video and go ahead and do the middle one. How'd you do? Most people miss this step right in here. Trying to find a better, there we go. Most people miss this step right here, where they forget the plus and minus. When I take a square root of a variable to clear the square root and the squared, I must make sure I keep the plus and minus. So now let's find the inverse by using a table, tabularly. So I've given you the table for the parent function of a quadratic. This is the graph y equals x squared, the parent function of the quadratic. This is the easiest one ever. So I'm going to just make a new table. So how do we find an inverse by table? All we do is we switch the x and the y. We just switch them in the table. So -2, 4 becomes 4, -2. -1, 1, 0, 0, 1, 1, 4, 2. We just switch them. So what I want you to see is what this graph looks like. So -2, 4, and again I'm freehanding this, -1, 1, 0, 0, 1, 1, 2, 4. And then we've got 4, -2, 1, -1, 0, 0, 1, 1, 4, 2. So we can see that this graph is a function, and we already see that its inverse will not be a function. Well, let's test it. This graph is not a function, which is the inverse of this graph, but it itself, its inverse, would be a function. So vertical line test tests whether the graph is a function. Horizontal line test tests whether the inverse would be a function. This green graph and this red graph are inverses of each other. Notice if I now switch all of this table to find the inverse of this table, I would just end up back at this table. Remember, this is the do and the undo. Really quickly on the bottom of this page, I want to show you how I check an inverse graphically. I check an inverse graphically by reflecting over the line y equals x. The line y equals x is the parent function for tables. It has the point 1, 1, 2, 2, 3, 3, 4, 4, -1, 1, -2, 2, and so on. And if I draw this parent function through here freehand style, not quite perfect, you can see that if I fold my paper over on this line y equals x, that the green one would fold over to the red one. That's how I test an inverse graphically. I reflect it over the line y equals x. If you remember from the slide where we found the inverse of a function algebraically, this example right here was the one all the way on the right, and this was the inverse that we found. In order to verify that the two functions are inverses of each other, we have to take a composite. For those of you that know what composite wood is just a mixture of woods together to use a cheaper wood with a harder wood and make it cost not quite as much, but make it kind of strong. So that's what we're going to do. We're going to mix one function with the other. We're going to mix the function with its inverse. That's what a composite is. So the technical way of writing this is to say that I need to find what f of g of x is, and I need to find what g of f of x is. So now you're asking what's f and what's g? Well, functions really are referred to, as g of x or f of x. We don't typically refer to them past algebra 1 as y. So we're going to refer to this one as f of x and this one as g of x. And we want to know if f of x and g of x are inverses of each other. So the first thing we're going to do is we're going to put g of x into f of x. So we're going to take g of x and put it into f of x. And I always substitute into the x. So I did copy it from the first page wrong, so I'm going to make sure I fix that before I do this. So now I'm going to take the green function and insert the red function in for x. So I just took this function and I plugged it in for x in parentheses right here. And I'm going to simplify this. So I'm going to distribute the 3. 3 times 1/3 x squared gives me x squared. 3 times negative 1/3 gives me negative 1. And then I have plus 1. This simplifies as x squared. The square root of x squared is x. Now let's look at what happens on the other side. I'm going to take this 1/3, but now what it's saying is I want to take f and put it into g. See how f is inside of g? So I'm going to take f and put it inside g. So let me just make sure that we change these letters up here. We're going to call this guy g of x, and we're going to call this guy f of x. So now I'm going to put in, I have the x squared, but I'm going to plug in my f of x. And I'm going to square it, minus 1/3. And when I square something that is completely covered by a square root, the squared and the square root cancel, which is nice. So I'm going to be left with 1/3 3x plus 1 minus 1/3. I'm going to distribute x plus 1/3 minus 1/3 x. So these both simplified from their composites down to x. From the composite down to x. To verify that two functions are inverses of each other, this must happen. If they don't both simplify down to x like these did, then they are not inverses. We have just proven that ours are inverses.